Okay, welcome to this session. As I said earlier, it's a more popular talk than I thought it would be. I thought there'd be maybe 5 people interested in boot up time. But thank you for spending your time here on this topic with me. My name is Tim Bird. I always throw the abstract in so that when someone's looking at the slides, 2 years from now, they have an idea what the talk was supposed to be about. But this is the outline that we'll use. We'll talk a little bit about why there's no upstream boot time regression test already, and then just go through this list of things. I'll show you my boot time test and some of the issues found. And towards the end, I'll explain why my test is also not upstream. But I think you'll get the gist of it. So why is there no upstream boot time regression test? Well, actually, there's only one other boot time test in the entire world that I'm aware of. It was done by Laura Now, and it's based on ftrace, and it was not accepted upstream. And so if you look, there actually is a lot of stuff upstream relative to boot time, right? We have print K timestamps. We have all kinds of instrumentation tools, initcall debug. We have boot graph, and there's boot chart. There's all kinds of tools, but they're all visualization tools. They're not tests, right? So a test is something that yields a pass-fail result. There's a couple of seats up here. You can use the reserve seats, and over here. So, so in other words, examining boot time, there's all kinds of tools, but actually testing boot time, that's left as an exercise for a human, right? And so, and even stronger statement than that, I'm not aware of any automated performance test upstream, right? So I don't know of any performance test. Again, there's all kinds of benchmarks for lots of different things in the Linux kernel, but they're not tests. They don't yield a pass-fail result. And so there's kind of 2 parts to this absence. Let's see, I think that's okay. There's kind of 2 parts to this absence. Why is there no shared test that the industry is using? And why is this thing that doesn't exist not upstream? So why is there no shared test? Boot time code paths are going to vary widely from machine to machine, right? So each machine is going to have different speed of its processors, different CPU count, different amount of memory, different peripherals that are initialized. And so that's due to both hardware differences, CPU speed, memory size, storage, and then also the configuration is different, right? So the features that you put in the kernel affect the kernel size, which affects the load time for the kernel image. And also, the requirements are different. The thing that you need to get to quickly is different depending on your use case, right? In automotive, it's always the camera, right? I got to get the backup camera up in like 500 milliseconds or a second or whatever it is. But for different use cases, like in SpaceX, their use case for rebooting is quite different. They're very complicated. They have these fault-tolerant configurations of nodes, and they want to reboot some nodes if it gets hit by a gamma ray. But anyway, and so even for the same types of hardware, like if you're doing a camera, it could be connected to your system via different bus, right? So you may need to bring up the USB bus, or you may need to bring up Ethernet, right? Or something else. So in general, the non-probing buses like SPI or ITC come up really quickly, whereas the probing buses like USB or PCI come up very slowly. And so you can kind of think of this, what you need to get up quickly, as the workload, right? And so a lot of times benchmarks consist of measuring some workload. In the embedded case for boot time, what it is you're trying to get to quickly is your workload. In any event, the result of all this is that no single test can capture all these different use cases, right? So that's why we don't have a shared test that everyone is using. Okay, so why is there no upstream test? Well, the first thing you need for a test is you need consistent, generalizable pass-fail criteria. And you can't do that because it's the curse of embedded, right? Because everybody's doing a different thing, right? And so it makes it much harder to share. But there are also some boot time specific issues, right? So not all time delays are within kernel scope. And in fact, part of my findings here is that most of the time delays are not within kernel scope. They're either in the bootloader, the firmware, or they're in user space. And there's also this kernel boot time blind spot, which is a real problem. So there's a portion of the kernel boot that occurs before the clocks are initialized. And I've found in my own testing there's about 60 to 150 print-K messages get spit out with a timestamp of 0, which is not that useful for testing. And it represents between 100 to 400 milliseconds of boot time. And if your camera needs to come up in 500 milliseconds, that's a significant portion of your total boot time budget. And the same is true for other types of instrumentation, right? So there's early console or there's ftrace. There's all these kind of trade-offs you have to make. If you want to test things by looking at like timing the serial port, well, then the print-K messages consume too much time, right? And so the best measurements would actually be from external hardware. That would give you consistent results that are not depending on the kernel self-instrumentation. But that would, again, be lab-specific, right? You'd say, OK, put this logic analyzer and watch these lines. But that's not going to be a generalized solution. OK, so we should just give up. This is too hard. No, let's look at some of these things and see if we can address them. So here's a proposed solution. My goal is to produce an upstream test, and I want to use reference values, and I want to keep those reference values separate from the test, and I'll talk about that. That means I need to store them somewhere besides upstream. So this has been discussed in previous attempts to do this, and it's been deemed that it would be infeasible to try and keep a vast array of these data files up in the Linux source tree. And then the ultimate goal here is automatic testing, right? With automated reporting to a maintainer. It's like, hey, your initcall in, like, say, the networking subsystem, somehow it jumped in time. What happened there? And so that would help us keep a check on boot time in the upstream kernel. So here's my boot time regression test. So my regression test consisted of some simple steps. I measure the values, I compare with reference values, and then I report regressions. And I haven't done that last step yet. I divided the work into several steps, several different programs. I have something called grabbootdata.shell for data collection, the actual test itself, which does the comparison. And then I have something to manage reference value files, find matching reference value. So let's talk about those. So grabbootdata is a shell script, and it does the data collection, which it sounds more complicated. It's really just dmessage, right? So I'm just grabbing a bunch of stuff from the machine. But I also collect a bunch of other metadata about the machine. So I grab the uptime, kernel info, info about the distribution, the config file, the amount of memory you have, the mounted file systems, a bunch of about proc CPU info. And I'll get back to why I want all that metadata in a bit. And the other thing it does is it checks that you have put initcall debug on your kernel command line, which is kind of the thing that turns on a bunch of this instrumentation for boot time measurement. So one of the important attributes is it's a simple POSIX shell script. So it can be run on any embedded system that has core utils. It really needs only a couple of tools that are pretty much guaranteed. Basically, if you have a BusyBox-based system, it'll run, right? You don't need a fancier system. Of course, it'll run, obviously, on bigger systems. And it saves the boot data file locally, but here's the tricky thing. It also automatically sends the data to a machine under my control. And we'll talk about that. It uses curl, and if you don't have curl, some deeply embedded doesn't have curl or doesn't even have networking, you can extract that boot data file, and there's a command you can run on a host to submit that data. So because I'm saving this data on a shared machine, a shared repository. You have to specify a lab and a machine. You can just make up any name you want here, but it's very simple execution. You just run this tool as root because there are some of the operations require it to be run as root. And you can look. This shell script's only like, I don't know. I think it's like 50 or 60 lines long. It's not. It shouldn't be scary. You may object to it sending data upstream, in which case there's a way to run it without sending the data. But it produces a file with all this data in it, and you can get help for it. And there's some. I have not put this in a GitHub repository yet. It's so simple, I didn't think it needed one, but maybe I need to put it in one. So what is in terms of what we measure for the boot time test? We measure initcall durations. That's easy because they're printed out. And then we also measure something I call regions, which are defined by print Ks. So I look at print Ks. I try to determine the delta from one print K to the next, and what I have a system to categorize the print K, indicate what subsystem it applies to, and then I have this basically a state machine that keeps track of when a region is starting and ending, and so there's some tricky things there that I'll get back to in a bit. But one of the things is that I actually am accumulating values, right? Because there's several operations that are performed relative to like storage during initialization. So if I want a kind of a storage accumulation of the durations for storage, I need to aggregate some region durations. It was a little bit hard to find unique regexes for some of the print Ks, but I'll come back to that. So the actual test is called boot time regression test. This processes that data file that was created. It compares results with a reference value file. And it's actually a very simple thing. You give it the name of the data file, the name of your reference value file, and it produces KTAP format. And one of the things that's key about it is it has to determine what constitutes a regression, right? So it's different with a pass-fail test, a functional test. Usually you look at a value that you got back, you look at the expected value. If it's different, then you're done. But it's a little bit trickier than that. There's lots of kind of things that can affect the value for a benchmark that don't necessarily constitute a regression. So you can just compare, is the value I got different than the greater than the previous value? Did my duration expand? That's too simple. You get lots of false positives. I did plus minus 5%. And then I finally settled on, and I'm not sure this is the final good rule, but my ultimate rule was plus 5% only if it's greater than 30 microseconds. And so weed out kind of small changes, right? I originally, I had done support for a configurable rule that the user could adjust, and I may still go back to that because there may be certain init calls that kind of need their own rule. Anyway, during boot, there's kind of less of these things. Like if you're measuring storage or you're measuring graphics, there's a lot of stuff that can happen on the machine that will cause variations. During boot time, we have less of that. And so the jury's still out on whether I need to do a customizable pass criteria. So this is what the file looks like, heavily redacted. You'll notice immediately you can see some problems, right? The very first thing is the first 100 or so of the init calls come out with 0 timestamps. That's a bummer. Okay, that's not useful for measuring those. I had this devlink init duration was exactly 4 milliseconds. That's suspicious. And it was 0 in the reference file. Well, that's also suspicious. So, okay, so that I got to investigate that one. I had this one gent mod init. That's the jitter entropy module. Came out to 32 milliseconds, which was what I was expecting. And it was not found in the reference value. Okay, so the reference value file didn't have a value for that one. And I can explain why that happened, but I won't anyway. And then the only real thing in here was this init call phi GMI2 cell driver init, which had a delta of 114 microseconds, and so that went up a little bit. And whether or not whether or not the maintainer would care if he increased his time by 114 microseconds, That's an open question, right? So the problem with a lot of these things is it's death by 1,000 cuts, right? Someone says, well, I can add this extra operation during boot time. It goes up by 100 microseconds. Surely no one will care about that. It's like, well, when you've done that 100 times or 1,000 times, pretty soon you're delaying your boot time. Okay, let me check the time here, make sure wow, I'm way off. Okay, so some of the issues I found. Identifying boot regions based on print K was hard. There's no common print Ks you can use across all platforms. I'd hope that there were some, like, that someone would say, oh, this is the start of storage initialization. This is the start of memory initialization. That's not happening. The print Ks in the kernel are very ad hoc. The aggregating the durations, I thought that was a good idea. It turns out that's not such a great idea. That's bad for reporting. It tends to hide the actual location of where the delays are. There's deferred probes in the kernel, which means that a lot of times the probe duration, the actual long period of time that happens during an init call, that turns out that happens completely outside the scope of where the init call function is. And then, of course, the timestamp blind spots gives you tons of zeros, which is a problem. And that's one thing we'll talk about that in the boot time BOF this afternoon. There's some projects to try and fix that. And then also, this is a test framework issue. It requires that you boot the kernel with initcall debug. And that means that if you're going to automate this, you need to have automated support for command line modification. And I don't know, maybe Lava and kernel CI did this, but the tool I was using, I have that support, but it's a bit of a pain. Different boards support modification of the command line different ways, right? Different bootloaders. The best one is Raspberry Pi, where it's just command line.txt, and you can throw something in there, and that'll come up in the next thing. Otherwise, you're modifying grub config and whatever it is. So again, that's a thing that's specialized per board. So let's talk a little bit about reference values. Let me see how I'm doing on. Oh yeah, I'm already 8 minutes behind. Okay, so I'm going to go faster than I should. Reference value files. These are just files that contain the values that are known good, right? So that your boot time should not exceed these metrics. And you have to have a reference value file. You have to have some expected value in order to produce a pass-fail result. So what are some of the attributes? What is the format? How is it created? And where is it stored? So I decided to have the reference value file be the same format as the boot data file. So I can take any boot data file from a previous run and say, that's my set of reference values. That's easy conceptually. I experimented with a different system where I just stripped out the values and stored those. But there's a bunch of reasons why you want to keep the metadata associated with those. I'll get to in a sec. So it's easy to create. It's nice to keep the metadata with it. And I already had a parser for it, so that was good. So to create a reference value file, you just create a symlink in my current system and add the string ref-values to the file name. So that's pretty easy. So where can they be located? They can be located on your current system, and in fact, one of them has to be located locally at the time of the test. Well, let me get back up on that. You can either have a set of reference value files locally, and that allows you to run the test without having to access the internet, and you have complete control over which reference value files are used. Or on my boot data wiki that I created, I have a set of reference value files, and you can download one. You can either download those ahead of time, or actually at the time of the test, you can tell the test to go look at them, find one that's a good match, download that, and use it. So the goal with having pre-configured reference value files is so that that experience or knowledge about what constitutes a good value, like does everybody know how long the storage initialization is supposed to be? Is it 10 milliseconds? Is it 100 milliseconds? Is it 5 milliseconds, right? So a lot of testers don't have that knowledge. My idea here is that if there's some pre-existing reference value files, users can use those and trust that someone who's an expert on that board, hopefully like the board manufacturer or someone, knows what's supposed to be a good value for those data points. So I have a tool that allows you to match to find reference value files. It does so with a scoring system. And it can query both a set of local files, or there's a command you can run to query the set of reference files on the boot time wiki. And at test time, if you just want to trust that the test will give you a correct reference value file, you can just tell it to do it automatically, download one that's appropriate. So there are still issues with reference value files, right? So sometimes variance is not caused by some deterministic thing. Sometimes some durations are affected by timeouts. And so like when the init call was started relative to the machine timer tick, that may cause variation in delay. And there are some ways to mitigate this, like averaging results over multiple boot times. But the other way is just to allow higher variance for a specific init call or region. And the other thing is that the way I've structured it, it requires a full data parse of the boot data file. That is not a problem for an individual test. These things are parsed in under a second. But on the boot data wiki, if we're doing a whole bunch of analysis, it adds up, right? If we're doing 100 files and looking at that. So metadata matching. So the boot data files have a bunch of metadata to match. And the reason this is important is even if you're testing on the exact same machine, if you change a kernel command line parameter, that can drastically affect your boot, well, drastically, by 200 or 300 milliseconds can change, your test. So even the slightest deviation can end up changing the results. And so you really need to capture a lot of metadata in order to do this matching. And what you really want to do is you want to make sure that your machine environment the device under test environment matches the environment that was used for for creating those reference files. So I have a bunch of tools to manage this metadata. My boot data parser parses metadata and also synthesizes some metadata from like the config and the kernel version. Anyway, I have all these tools to deal with it. This is an example of a scoring output. So I was running this on a BeaglePlay result. What you do is you give it your result file with its metadata. It looks at all the other result files with their metadata and tells you which ones match. So you'll notice that TI bootlib SKM62X, that's about 5 lines down there, has a pretty good score. Other tests on my same machine in my same lab had really good scores, 72,000. But there's other BeaglePlay boards that were in the 50,000 range. And then if you got really desperate, you could use a reference value file for the Raspberry Pi 4, which is a completely different board. But so I'm still working on the thresholds and the weighting for the config parameters. But anyway. One of the features that my tool has is that you can get a detail of why the scoring was what it was, right? So you can say, well, this was the same lab, the same machine. It's the same architecture. You get 5,000 points for being the same architecture. If all your configs are the same, you get a pretty high score. A little bit missing there for config differences. And then things on the kernel command line. You get a bump of 200 if your BOGO MIPS matches. Anyway. Okay, so results. Let's talk about results. Let's see how we're doing here. Okay, so findings and regressions found, and then some of the new tools developed for this effort. So I did find some regressions. Okay, so I had to go back a ways. I wanted to get a sufficient distance from my reference values to my current test. So I had just a desktop machine that was running 5.15. And I upgraded that, went from Ubuntu 20.04 to 24.04, and the kernel went from 5.15 to 6.8. And I found 10 init calls that were more than 10 milliseconds longer. So kind of my threshold is if something increases by 10 milliseconds, that's something we need to look at. Okay, so that's upwards of 1 or 2% of my budget. And so the way you do that is it's really easy because stuff is being emitted in KTAP lines, and I put the delta on the line. You can just actually use simple command line tools to detect those. So here's the actual delta regressions on my x86 desktop machine. And if you look in that, you'll see some really goofy things. Like the input LEDs in it went from 541, used to be really slim in 541 microseconds. This is about the middle of the pack there. Went to 30 milliseconds. Like, what the heck happened there? And so there's a lot of those where a substantial amount of increase occurred. So yes, you can actually find regressions with this test. So I only found one regression well, I haven't done all my analysis yet, but on ARM64, there's something called gentmod-init, that's that one I was talking about, that does the jitter entropy, went from 30 milliseconds to 50 milliseconds, and I can't remember I think it was from kernel version 6.8 to 6.12 or something like that. And so what are your solutions? How do you fix this? Well, one is to don't use that module. Okay, you may or may not be in a position where you can do that. Another solution is to use deferred init calls. There's a patch you can get that's out of tree that allows you to take a module and not run it until later. And then it turns out, though, that the author of this added some config options that allow you to control the quality of the entropy and the size of the entropy pool. So there actually are command line parameters you can use to tune that. And that's the type of thing, how are you going to know that, right, unless you have some information on it? I expect to find a lot more regressions with additional analysis. So just some of my findings overall. Defining boot K regions with print Ks alone is quite hard. There's not enough common print Ks. I originally wanted to see if I could do this without having to modify the upstream kernel at all. I didn't want to add additional print Ks because that adds overhead. So I may switch to an ftrace-based solution, but again, ftrace has the same problem with this blind spot where ftrace isn't up early enough. And so, print Ks, turned out that print Ks was not the optimal thing, but it is there. And actually, as a human, that's probably what people are doing, right? They're looking at the print Ks, they're doing the delta calculations themselves, and they're figuring out, well, this is a long delay right here. What's going on in there? The problem is, because it's print K, you don't know. You have to go find the print K in the source, the starting print K in the source, the ending print K in the source, and figure out, okay, well, what happened code-wise in between those two? That's a difficult problem. So I'd like to be able to drill down. It would really be nice if I'm using ftrace, like if I find out a certain init call is taking longer, to be able to get the ftrace from when it was shorter, like a deep dive into that function trace when it was shorter and when it was longer, and then it should be pretty easy to find out where things went wrong. All that diagnostic, that's independent of the actual detecting the regression. So this test detects the regression, doesn't do the deep dive to diagnose it and come up with a solution. One thing at a time. Got to get the test first. So some of the tools and resources that I created for this were, there's 4 programs that are 4 programs and modules that are related to the test itself, which are grab boot data, the boot time regression test, find matching ref value, and boot data parser. So that's the test itself. But I ended up doing a whole bunch of other tools. I did print K analysis tools. I have this tool called show boot data that will extract individual pieces of metadata or of init call durations and show you those. You can pass it multiple files. It shows you kind of a history of those values over time. And then show delta, that's already upstream, but I've made some modifications to it. And then the boot time wiki. I got to talk about the boot time wiki because I did a whole bunch of work on this. So I created my own upstream repository to hold this data and to hold the reference files and to hold the test results. It's a long story why I didn't do KCI-DB. I should have, but anyway, it's a long story. I had control over this, and I knew a lot of this would be in flux. So that wiki has a whole bunch of stuff. It has visualization and analysis tools. It has management tools for managing reference value files. It can show you reports, graphical reports, as well as textual reports of the top 10 initcalls, how long they took on a particular test run. This is one of the pages on it. So it shows you, a list of the files for a particular, runs on a particular machine, and you can get different reports. And you can compare that boot data report with another report. That's useful for determining which file you want to identify as the reference value file. Okay, so next steps. And the reason I'm hurrying, I know I'm not right at the end of my time, but I did want to leave time for some Q&A. So I do need to make a GitHub repo for the test and the related tools so that people can play around with it as well. I would really like to gather more boot time data from more platforms over more kernel versions. I haven't even addressed the reporting side yet, so I need to automate the reporting. As soon as I'm comfortable that I'm producing reports that are not false positives and that actually have useful value, I'll start sending reports upstream. But I need to finish defining boot regions. I got kind of stuck on that. Better analysis of deferred probe. There's actually a patch that's been, an RFC patch that's been submitted upstream to instrument probing better to handle that. And support extra kernel regions, right? So this is all focused on the kernel, but there's work afoot to gather data from the bootloader. And I wondered whether I should do systemd analyze blame, which gives you the unit file durations. I haven't looked at user space or the bootloader yet. So this is just a start on the kernel itself. My ultimate goal here is I would really like to write a boot time tuning tool. The fact that every company that works on boot time basically starts from scratch with their own boot chart or their own boot graph, and there's no sharing of information. There's no like, well, this shouldn't have been this long, or this is an easy way to tweak this, to tune this to boot up. I would really like an automated tool that helps a developer go through the boot time reduction process, right? We won't get, we'll never have default kernels coming out of Linus Torvalds trees that are, booting in 500 milliseconds. That's not going to happen. But we can make it easier for developers to find the things they need to adjust to fit their product. That's my ultimate goal. Okay, so I need to start reporting and fixing those regressions. I need to refine the grab boot data tool. I found out pretty soon that if it shows up without the config or the kernel log buffer was not big enough, and so I dropped a bunch of data, or the kernel was compiled with no symbol support, turns out those reports are not as useful. So I need to do some extra data checks. So here's my big ask. If you are working on boot time, please, please, please run grab boot data shell on your own system and generate more data for me, okay? And so that will really help me out. That's it. So thank you very much, and I'll open for questions. Yeah. Thank you. Yeah. Do we have a mic that we can run to the audience? Anyone back there? Okay. Well, just go ahead, shout, and I'll repeat.
So I'm working on code coverage patches for the kernel for LLVM. And I think if we added a section that the code coverage, you have an advantage here because your init code generally only runs once.
Right.
Code coverage is about aggregation, so you can't keep, you can't track. But I think because your code, the code you're interested in, only runs once, if we added another section in the code coverage that kept track of when the last time that line of code was triggered, then you could use an existing code coverage tool to get the exact information you want.
Okay, so I'm going to have a hard time repeating that for the question was about code coverage and whether code coverage tools could assist with this.
If we add a section.
If you add a section for time. Yes, while you were speaking, I thought of some issues. Now that I'm giving my answer, I can't think of them. But yeah, it would be really interesting. Oh, the main thing is that extra instrumentation at boot time heavily interferes with your boot time. And that's what, like, I thought, I'll just use ftrace and function tracer with ftrace. I got a 2 gig trace, and it slowed down to like 5 minutes, And so you have to be careful with the extra instrumentation. That's one of the issues. But no, I think that's an interesting proposal. Yeah.
Any chance we can kind of avoid the UART printk based time calculation and then go with some default timers that we can?
Yes. Okay. So the question is, can we avoid the printk timestamp, which comes from the time system of the kernel, and use something like the cycle counter? And the answer is yes. I already played around with it. I didn't have time to put any results in here. And I have a slide in my BOF presentation about that. I know that the unified boot log thing that Vishnu is working on, TI is working on, is looking at that as well. So there are, on almost all modern systems, there is a stable cycle counter that is initialized from hardware inception. And it's really useful for finding this type of stuff, but it's not reported anywhere. And so one of my proposals is just to add a couple of print Ks just with the cycle counter, independent of any other like tracing or buffers or whatever. It's very, very low overhead to get. It's a single instruction, but you do have to calibrate it after the fact. And so there's issues, but that's not a hard problem relative to the problem space. So yeah, I definitely want to pursue that. All these ones, it was driving me nuts when I would see all these things with 0 timestamps. It's like, well, it's like a whole bunch of data I'm not getting any information on. I'd like to either put it into ftrace or put it into printk itself, or somehow instrument something, but.
If that gets started very early, probably by the wrong code, or the first code that executes, if something like that gets started, then we can actually instrument the entire flow. Like you do
right.
bootloader and the kernel.
Right. Yeah, and so ARM64 has it, x86 has it, RISC has it, so, and even some ARM32s have it. I don't know how many people are interested in that, but like there are these cycle counters that are stable, and they don't need to be hyper accurate, right? So they actually get initialized. There's some calibration that's done during time init that tries to calculate, exact duration so that it can use the TSC as one of the timers in the system, but that's not needed. We're looking at microsecond granularity. We don't need that type of precision for for this particular use case. Any other questions? Yeah.
Have we considered using an emulated CPU like with Q to get normalized values of instructions and execute it?
The thought has crossed. Okay, so the question is, have we considered using QEMU to get like normalized values for instructions? I have thought about using QEMU. I don't know if in the same way that you're describing, but I did think a lot about whether or not I could synthesize reference values. Like if I characterized the machine sufficiently, could I actually just calculate what the value should be, right? Do I know that like some particular initcall is going to take 1,000 cycles, and could I use BOGO MIPS to predict what the value should be, what the duration should be? And I don't know. I kind of have. That's on a back burner, And of course, the problem with doing wall clock timings with a virtualization system is then you're subject to the host machine and all its variations. So, but yeah, the idea I think your idea, what you're saying is to actually calculate like instruction lengths or something. That's interesting. I probably don't have cycles to work on it though, so anyway. Any other questions? We've got 2 minutes. If not, thank you very much for your time.